now, so I got to make sure I don't say anything that gets me in trouble. That way it'll be on tape. We don't want that. It'll be bad news for O'Grady. I'd have to get a real job. I guess that's insulting too. Actually, I love this. This is fun. If just one of you per year gets something out of what I babble about, it'll make me happy. All right, so anyhow, what we've been discussing is the last two classes. Let's sort of put this, to tell you what we've done. So the last two classes were all about motivating. Boy, that is very sloppy writing. I apologize. Let me erase this. You guys deserve better. So the last two classes were, did I get this correct, my grammar friends? Were all about, that's what they say in Canada, about, all about motivating probability. So we spent some time talking about coin flips. We spent some time talking about rolling dice. Is anybody in the waiting room? No, that's good. And we'll mute some of you in case you want to scream and yell. But you can always unmute yourself if you have something to say. And then we talked about this other experiment that I keep bringing up, but I haven't said much about, was this throwing this cup, as you guys like to call it, the flip cup game. And the point of all these things, and this is probably not the last time I'm going to say it, but it might seem like I'm becoming repetitive. And I don't want you to think I'm repetitive. I'm trying to prove a point. And that is that there is an intuition with certain games or certain experiments. And this intuition is one that we can quantify numerically. And then we have other games or other experiments that there's intuition what's going to happen, but we can't quite quantify it. And it doesn't just have, when I use the word game, I'm using that in a very general sense. When I use the word experiment, I'm using that in a very general sense. Like, I don't have to just talk about flipping a cup. I could say, okay, whose commute do I think is going to be longer to college? Someone who lives an hour away from where, or excuse me, 20 miles from where they go to school, or someone who lives 300 miles, right? I might not be able to quantify in general how long it's going to take you to go, but my intuition tells me the closer you live, the likely it is your commute is less. Do we understand that? But I can't specifically quantify it, at least not without some other work. And so what we have to do then is, if we want to develop some sort of science that we're going to call probability, if we want to develop it so that it's useful, our development has to do two things. It has to include the special easy cases that are intuitively making sense to us, like flipping a coin. If the coin is fair, we expect heads just as much as we expect tails, right? If I have a dice, just one of them, and it's six-sided and it's fair, I would expect that any one of the numbers 1 through 6 is equally likely. So if I develop this axiomatic science that I'm going to call probability, this branch of math that I'm going to call probability, I better develop it so that that stuff can be quantified, as Phil said. I think, Philip, you were the one, I don't mean to pick on you, but I'm pretty sure you said it last Monday. You know, we want it to be able to quantify it the way you suggested in those simple cases, but we also have to develop it so that we can apply it to more complicated, more realistic things. Like, obviously flipping a cup ain't that realistic, but something like, what's the likelihood a sick patient survives on this medicine? Or what is the likelihood that your tire doesn't get flat? Yeah, right. That's actually a good one, right? I risked that. I ran into the tail risk. Why? Because I waited too long to change my tires. That's a good point. No, and it's funny. Have you ever bought tires before? Yeah. They have a tread wear. They have these things where they say this tire should last you this many miles if you treat it properly. Right? Do they just make that number up? No, right? And in fact, these manufacturers, what they do is they run all kinds of experiments and tests so that they can be confident, say that there's a 99% chance that tire makes 50,000 miles or 40,000 miles, depending on whatever they you know. They want to know that there's an 87% chance that if you have to stop in 30 feet at a certain speed, it's going to happen. And so what we need to do, and that's actually a great analogy, good by you. It's like we're on a team. We need to develop a theory of probability so that we can generalize the simple ideas in a way that we can answer the real world questions like what is the stopping time on average for a tire? If I'm going 70 miles an hour on average with these tires, how many feet should I go before I come to a complete stop? That's an important thing. If I inflate my tires to the PSI that the manufacturer tells me to, how long should I expect them to last? On average. I mean, these are things in the real world we're interested in. And it all starts with the simple things of flipping coins and rolling dice. Or it starts with something like everybody here knows what a deck of cards is, correct? We're all familiar with a deck of cards. Maybe you don't know that there's 52 of them and there's 4 suits, and that means there's 13 of each suit, and then there's a 2 through a 10, and then there's a jack and a queen and a king and an ace. And so studying things like poker hands or pulling a card randomly, or if I have a bin full of colored marbles, what is the probability I choose this color followed by this color? Or what is the probability I get 3 heads in a row if I toss a coin 100 times? Answering those questions help us develop a theory that can hopefully, in practice, not all the time, but hopefully help us answer real world problems. Like, will this stock make us money? Will it lose us money? Will this new medicine, will it work? Will it not work? Will these people who we give money to through a loan, will they pay us back, or will we have to eat the money because they default on it? Okay, so hopefully you keep these things in the back of your mind when we do what we're about to do now. And that is, we're going to start doing some sort of, I don't want to say scary math, but we have to start putting some actual sort of, how do I say it without scaring you? I don't want to say algebra or formulas, but we have to put some sort of some sort of rigor, some sort of precision, some type of precision behind what we've been talking about. And that's what we want to do now. So before I do that, does anybody want to ask a question? Does anybody have a comment? You can say anything you want. Going once, going twice, sold to O'Grady. No, okay, cool. Well, good, then I ain't gonna answer anything anyhow. I kid, of course, I kid. Nice turnout today, by the way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Almost the whole shebang, but not everybody. All right. So what we want to do now is we want to write down in English sort of what I've sort of said, and then we are going to start doing some, as I believe Philip said, some formulas, which not everybody likes. We good? They always say if you ask a question, you're supposed to wait 10 seconds to see if the audience wants to finally ask you anything. Okay, so let's get started then, and let's say it like this. So here's our goal. Our goal is to develop probability, and the fancy way of saying this is in what we say an axiomatic way. And this is how, math is done this way, by the way. You don't realize it. You did it in high school when most of you, I would imagine, studied geometry. At some point, you probably had to take a geometry class where you studied things like, here's the 5 axioms and the 5 postulates, and then you had to prove these little, they usually do, and they call them 2-column proofs, where you might remember things like side angle side and similar triangles. Most of you probably had nightmares of that, so you probably got it out of your memory forever, but I'm pretty sure that's part of the high school curriculum in the United States. And even in algebra and other classes you would have taken, we start with a certain set of rules that we call axioms. And often these rules are very common sense. I know that if I have, I know that if I have 3 markers in my right hand and 1 marker in my left hand, that I have 4 total. And it doesn't matter which order I add them up, right? So numbers have like certain inherent properties. This is what we call commutativity, that when we add, order is irrelevant. And then there's other things like associativity. And these are all these things that we just assume. And from these assumptions, we develop a sort of theory. You know, in algebra, you learn, you know, they don't tell you this, but you're developing this notion of how to solve equations, certain type at least. And so here we want to do the same thing, is we want to make a set of rules, and then from these rules, we want to answer questions. And then we want to logically develop other types of things, which we usually call in math, we call them theorems. And what these sort of theorems allow us to do, these facts or these rules, what they allow us to do is they allow us to answer questions. And hopefully, under ideal circumstances, they allow us to answer real world questions at some point. Like how likely is my flight to remain on time? Or how likely is it that if I'm in a car accident, I am not hurt? Stuff like that. Okay, so here we go. So we've talked about this stuff, and now we want to give some precise meaning to it. So what we want to do is we want to start with some definitions. The first one is an experiment. So we're using this in a different sense than you might be used to it. A lot of people, when they hear the word experiment, they think of someone in a white jacket in like a lab playing with, you know, test tubes, or, you know, dissecting a frog. But we're talking, when we use the word experiment, we mean it in a much more broader way. So an experiment is any process that has a well-defined outcome. So, for example, flipping a coin is an experiment. Why? Because I can define an outcome. I can say, okay, there's two options here. There's a heads or there's a tail. But that's not the only experiment I might be interested in. I can change that experiment. I can say, I'm going to flip a coin 3 times. And then there's well-defined outcomes. What happens? Well, we listed these outcomes the other day. You can get 3 heads. You can get 2 heads and a tail, right? You can get heads, tail, heads. We listed them. There were 8 outcomes in that particular scenario. Do we get this? I don't think I get that. It's a kind of weird way of saying. So it's any process or process that has well-defined outcomes. So maybe I should say this even has a well-defined outcome or outcomes. So each trial of an experiment, and it might seem weird to word things this way, but we have to. So each trial of an experiment, someone just thought it blinked on me. So each trial of an experiment results in an outcome. And so we're going to make one more definition, then we're going to give you some concrete examples that match what we've done before. So suppose an experiment, as we've seen, has multiple outcomes. So the set of all outcomes of a given experiment this has a fancy name. It's called the sample space. So there's three words that you should be familiar with right now, or three terms, I should say. Experiment, outcome, and sample space. So let's think of these. Obviously, a coin flip is there's lots of ways we can have an experiment with coin. We can say I'm going to flip a coin once. We can say I'm going to flip the same coin 3 times and count how many heads I get. I can say I'm going to flip a coin 10 times and ask what's the longest run of heads in there. I can roll a die and I can ask what number comes up. Or I can roll 2 dice and ask what is the sum of each dice. So let's sort of dig into this example. Here's my experiment. I'm going to sort of list this in a weird way. So my experiment is toss a coin 2 times. So that's my experiment. What are the outcomes? The outcomes are, there's 4 outcomes. There's one option is I get heads, heads. The other option is I get heads, tails. The third option is I get tails followed by heads. And then the fourth option is I get tails followed by tails. And so then what's the sample space? The sample space is, and this is going to be new notation for some of you. I hinted at this before. Some of you may have seen this in algebra class or another math class. When we're describing a set, we typically use these braces. Does anybody have a question about this? Comment. So the thing to note is there are 4 outcomes in this experiment. Let's look at another one. So now, let's say the experiment is toss a plastic cup in the air. And record how it lands. So what do we mean record how it lands? Well, let's say side, top, or bottom. So the sample space has 3 elements. The sample space is it can land on its side, it can land on its top, or it can land on its bottom. So I hope it's all clear what I mean by this. I demonstrated it before, but we imagine, bottom would be right side up, top would be upside down. I don't want to turn it upside down because it'll spill. And then on its side would be on its side, right? That's cool with that. And once again, a key observation I would point out to you is that in our experiment on the previous example, we can quantify, at least there's an intuition for how likely each event is. Or I shouldn't say event yet, how likely each outcome is. Whereas in this particular one, I have a sense that side should happen more often than the other two, but I don't have any numerical sense of it. Do you understand that? Maybe you do. I'd happy to hear it if you have it, but I don't think there's an intuitive one that we'd all sort of agree on that says, oh yeah, that makes sense. Does anybody have a question about that? So let's do one more example because it's fun. This one might make your mind work a little bit. So here's one. Experiment is to toss a coin until the first head appears. So what's the sample space then? So this one's a little trickier for sort of when we're at this level. So the sample space, what does it equal? Let's write it down here. It has to equal, and this might seem scary to you. So the game could end. We don't know how long this game's going to take is the first thing, or this experiment could take. If it ends right away, that means I get a head on the first toss. But if it doesn't end on the first toss, that means I get a tails, then a heads. But if it doesn't end on the second toss, that means I get at least 2 tails before a head. Or I get 3 tails before a head. And so what you understand is that this space theoretically can't be counted. It can go on forever. I mean, technically, I hate to say this, but I can flip a coin and do this experiment, and it's possible that I might die before I get a head. It's unlikely, but it's possible. Does anybody have a question about this? Now, the first example is what we call classic probability. I mentioned this before. Why do we call it that? Because there's an intuition that all outcomes are equally likely. The next two, there ain't any intuition about that. In fact, with the second example, the cup, our intuition tells us they ain't equally likely. And even with the third one, our intuition tells us that we're probably going to get ahead sooner than later. Right? I mean, you could do that experiment 10 times and see what happens. Maybe I'll ask you to do that for homework. Do that experiment 10 times. I wonder if you'll ever get out of any of those 10, if you'll ever, how long, what's the longest time it's going to take you? You'd imagine it's only going to take you 2 or 3 times, right? Think about that. I mean, use your brain. You know, if you don't get a heads right away, you would imagine it's probably going to come on the second or third one, right? This is an important problem too, because this is sort of, this kind of idea can be generalized. What do we want to know? Imagine I manufacture something, a car tire. How long is it going to last? How long before it goes flat? How long before its tread wears away?
How long will it take you to make it?
Yeah. There's lots of questions like this. And so a very simple model for things like how long is something going to take before something else happens is this game. If I toss a coin over and over again, how long should I expect before I get my first heads? Yeah. What's that? Yeah, go ahead, do it. Flip a coin. Tails. All right, do it again. Heads. There you go. So it only took 2 tries, right? That's what we would expect. We would imagine. Our intuition tells us if we did it 1,000 times, it would probably happen between, on average, between the second and third. In fact, you can actually quantify this. Maybe we'll show you that eventually. We can give you the theoretical number. And you might say, what do you mean theoretical number? Well, remember what I did with the dice last week. I said, let's roll 2 dice. What do we think's the most likely outcome? And the most likely outcome turned out to be 7. And we actually counted how many 7s there were in the total sample space. And then we said, oh, there's this number. This is how often we think it's going to happen. And then I went to my computer and 100,000 times I rolled those dice. And then I counted all the 7s and divided it by 100,000. And I got almost the exact same number as the theoretical value. Do you get what I'm saying there? Okay, a simpler example of that is if you flipped a coin 1,000 times, theory tells us you should get 500 heads. So if I went to my computer and flipped a coin 1,000 times, very likely I'm going to get like 498 or 502 heads. Does that make sense? And it's even possible I get exactly 500. But it's very unlikely that I would have gotten like 106 heads out of 1,000. Do you understand what I mean? So there's this idea of what our intuition and what theory wants us to think is going to happen, and then what actually does happen. Okay. So if we know what an experiment is, and then we know what an outcome is, the obvious next question is how likely is something to happen? Just like we just said, if I throw a cup in the air, how much more likely is it to land on its side than its top or its bottom? If I am flipping a coin until I get my first heads, how likely is it that I get that on my second toss or my third toss, right? If I roll dice, how likely is it that I roll an 8? Well, if I roll 1 dice, it's impossible because it goes 1 to 6. But if I roll 2 dice, can I get an 8? Well, yeah, how likely is it, right? And so these are the questions we want to now get into quantifying, if we can. Now, we know we can't always quantify, but if we can, we want to. We cool with that? So, I don't know. This is the way my brain thinks, at least. You guys are like, shut up. Evil man, you. Okay. Don't hate, what do they say? Don't hate the messenger. I'm the messenger. Even if you hate the message, which is math. Like the late great Heavy D once said, I got nothing but love for you, baby. All right. Let's check the time. Let's see what's happening here. Okay, very good. So, let's put that down. Big question. How likely is a given outcome? So before defining this, let's remind ourselves we can quantify this if all outcomes are equally likely. So the way we do this is, first off, this is called, as I've said numerous times, this is called classic probability. So how do we do this, though? We need one more definition before we do it. So let me get a color here. We'll use this dark green. So an event. So now we're introducing a new word called an event. Is a set of outcomes. So before we give a definition, let's just remind you of what this means. We've done this already, although we just didn't say that what these were called. So let's look at an example. So a coin is tossed 2 times. So the sample space, as we already know, what is a sample space? A sample space is heads, heads, heads or tails, and then tails followed by heads, and then of course tails followed by tails. There's 4 outcomes. Here is the event of exactly 1 head. The event of exactly 1 head has 2 outcomes in it. Tail head or heads followed by tails. Bless you. Because you know, like, I am cold in here, by the way. I'm about to put my hood up. My fingers are cold. I shouldn't do that. And the Roni. Okay, so let's finally just make this definition that was sort of pointed out a few times by a bunch of you. Definition. So the probability of the event, we'll use capital E because I think the book uses that. So the probability of the event E is denoted by P parenthesis E and defined by the probability of event E is equal to the number of elements in E divided by the number of elements in the sample space. So it's often convenient to use symbols for this. So it's convenient to write the probability of an event is n of e over n parentheses s, where s is the sample space and n of s equals number of elements. So I'm using some words that some of you are familiar with, some of you aren't. We're using words like elements. So one of the things you should have all learned about in an algebra class, but I ain't fool enough to think you remembered any of this, is that in math, any collection of objects is called a set. And what we do is we can quantify in certain sets how many are in there. And so what we're going to do is we're going to let n parentheses of a set equal the number of elements in that set. And this might be confusing you right now, but once we do an example, I think it would be, oh boy, I almost killed myself. It'll be quite, I won't say quite easy, but it'll be, I think, a little more intuitively clear. Does anybody have a question about this definition? So look, the only time this makes sense is if we assume that every outcome is equally likely. That's the only way this even makes sense. So again, if I go to the previous page, this is classic probability. So let me repeat this. So the above definition makes sense only when we assume each outcome is equally likely. Which means this definition doesn't make any sense for something like our cup game. It doesn't make any sense for, is it going to rain today? It doesn't make any sense in, if I drive to work every day, am I going to get in an accident? It only makes sense under the most controlled scenario, that is, we have an experiment and each outcome is equally likely. Does anybody have a question about this? So it's also important to note that this definition takes into account what is your experiment. It's inherently in here. So it's not explicitly said here. The correct way of me saying that is it's implicitly in this definition. Because just take a coin game, for example, or a coin experiment. I can say flip a coin 3 times. Well, what is my experiment? Am I counting the number of heads? Am I asking, do I get 2 heads in a row at any time? There's lots of different experiments, and my probabilities are likely to change depending on how I'm constructing my experiment. Do we get that? Take something as simple as rolling a dice. If I roll 1 dice, 1 through 6, I could say, what's the probability I get a 3? That's great, but I can also say, what's the probability I get an odd roll or an even roll? Does anybody have a question, comment? So let's put those examples we've done in the past back into here. So what we did sort of last week, we sort of did in an intuitive way. We talked about it very colloquially. Colloquial. Colloquial. That sounds funny saying that. We talked about it in a very sort of, layman's way. But now we want to put what we talked about in the precise language of probability, at least classic probability. So here's what I mean by this. So we flip a fair coin 3 times. Let's look at the sample space. I'm no longer going to write sample space out. Let's note that we're going to use S. So what is the sample space? The sample space is one option. We get 3 heads. Then we could get heads, heads, tails. Then I can get heads, tails, heads. So those are all the scenarios where I roll a head first. Now what happens if I roll a tail first? Well, I could get a tail, head, head. I could get a tail, head, tail. What else can I get? Well, I can get a tail, tail, head. Now there's 2 more outcomes I have yet to list. So the first, I don't know how everybody's mind kind of works differently here. I don't know how you want to visualize all the outcomes. But there is a scenario where I get 3 heads. And so I listed that first. Then there's a scenario I do heads, heads, tails. Then there's a scenario I get heads, tail, heads. Is there any other scenario where I get a head in the beginning? Yeah. Yeah, head, tail, tail. Right? So notice I conveniently left a space there for you guys to remind me of that. And then, of course, the last scenario is where I get 3 tails. So my sample space has 8 guys in it, 8 elements. And so let's look right away. Let's note that the number of elements in my sample space is 8. Now, of course, at some point you're going to even have to just know it. I don't say know it. Someone, you might be sitting there at home or in here and saying, well, how did you know that these were the 8 guys? Well, chill out, Siri. Ain't nobody got time for you. Siri wants to talk. What did I say that made her talk to me? Number of guys. So you might say to yourself, how did I come up with this? Well, I'm just using my intuition. I'm saying, okay, in my head, let me flip a coin 3 times. What are all the scenarios that I can imagine? And I can't imagine anything else besides this. If you can, that'd be great. Now, suppose we wanted to know some things. We can answer lots of questions right now from this given information. Now, I'm just sort of, I could ask you these things, but instead I'm going to do some stuff. So let's say the event of, say, exactly 2 heads. We'll call this E. What is this? What's in this sort of event? Well, exactly 2 heads is heads, heads, tails, heads, tail, heads. And that's it, right? No, sorry, there's one more. There's tails, heads, heads. So there's 3 outcomes in this event. There are 3 ways that I can achieve this goal. I can achieve this goal by getting head, head, tails, or I can go heads, tail, heads, or I can go tails, heads, heads. That's the only scenario here. Okay, so what we say then, the probability of this event, the probability of E, which is, we'll write it out in English, which is exactly 2 heads, is equal to 3/8. Does anybody have a question about this? So something we need to sort of caution ourselves with. So we won't always be able to describe the sample space easily. And I'm going to put easily in quotations, because what I mean by that is, suppose I played a different game and I said, okay, I'm going to flip a coin 7 times and I want to know what's the probability I get 2 heads. Well, I can tell you this right now, you sure as heck ain't going to want to write out the sample space of flipping a coin 7 times. And you know the reason for that? Because there's over 100 outcomes in that space, and that's going to take up a lot of place. So there has to be some sort of systematic way, some sort of alternative way of maybe being able to visualize an experiment or understand an experiment. Do you get what I mean by that? So before we move on to that, I will say this though. So simple experiments. Such as tossing a coin, a couple times. Or rolling a dice. These guys should be understood though. So what I'm saying is, for you as a student in this class, you should know what the sample space is of tossing a coin 3 times. And you should realize it's not difficult to write it out. You should understand the sample space of rolling a dice in determining the sum of each guy. It's not hard. It's actually very simple. We drew it out for you. It's a very simple symmetric picture. You should have a visual of that, or you should understand how to Google it. So what do I mean by that? Well, let me show you. Let's go to, I need to find a web page. We'll go here. So sample space, hopefully you're all seeing this at home, of rolling dice. You're going to have lots of cute pictures on the internet that you can check out. Here you go. What is the sample space? Now you have to find one that's useful. You got all these cute pictures. So it's not hard to be able to determine this. I would encourage that you sort of have a way, it'll be useful because like I said, we're going to do lots of problems where we're talking about rolling dice or flipping coins. And the reason is these are sort of what we call the fundamental examples. If you're going to understand the basics of probability, you have to understand this. The fancy word for that is canonical. The canonical examples. So like this picture is a good one right here because it's telling you the sums. And what you'll see is there's only one way to get a 2. There's only one way to get a 12, right? However, how many ways are there to get a 7? Oh, there's 1, 2, 3, 4, 5, 6 ways to get a 7. How many ways are there to get a 6? 1, 2, 3, 4, 5. And so it turns out, if you think about this, you'll see that 7's the most common number. As we saw, what? We saw on Wednesday when we did the experiment ourselves. Well, I don't say ourselves. We had a computer do the experiment for us. So let me reiterate this. I think you guys should have, one of the things you should have in your back pocket, so to speak, is this sample space. You should have a coin sample space, whether when I toss a coin maybe 1 or 2 or 3 times. If I toss a coin 3 times, the sample space is 8. If I toss it 4, then it gets ugly. It's 16. It has 16 outcomes in the sample space. Does anybody have anything they want to say? Cool. Guess I don't either then. All right, so let's get back to some math here. And look, the best way to learn this, as I've always said, is for me to just force you to do it by giving you homework. Well, I'm not forcing you, but bribing you with points. And that's the call it, or that's not it. I guess it's the, well, I don't know. Is it the Western way, I think. Because like one thing I learned when I was in graduate school is a lot of universities don't do it like we do it here. Like in places in like England and in Asia, like you get like, you come and you sit down and you have homework and they don't even collect it or grade it. And then you just get a test at the end of the semester and your grade is based on what you do on that test. You guys will be screwed. But here we bribe you with homework points. We say, here, we'll give you 10 points if you do these problems. And you're like, yay. Right? Is that what happens? I don't know. All right, anyhow, let's think a little deeper about this. With the following. So let's do one more example here with the dice. Let's say, so a pair of fair dice are rolled and we count the sum. So what is the probability we roll a 7, and what is the probability we roll a 4? Now, when I say on the previous page you should understand the dice, that's what I mean. You don't want to have to draw this out every time. Now, the first couple times you do it, you should draw it out, or at least Google it and look at the picture. But at some point, if you've done it a few times, you should have a mental image of that picture, and it's not hard. I'm not saying memorize it. Don't go home and make flashcards or recite it during commercials or your favorite show. But I'm saying do enough examples where it becomes part of you, like 2 + 2 is 4. It ain't that difficult, I promise you. It just ain't. It's very symmetric. It's a very simple picture. And sometimes all you have to do is just write out the first couple guys, and then you can fill the rest in mentally. I promise you. Why did I say we roll at 7? How about we say we roll a 7? You guys should fire me. I'll tell you what. Should be fired. Can you imagine? What if they fired me mid-semester and they had to bring someone else in? Who would it be? Would you like them? All right, so what do we have here? So for our solution, here's what you need to note. The sample space has 36 outcomes. You should know this. Now, there's an easy way to get this. What if I told you that we're rolling 3 dice instead of 6 or 2? Well, then each dice has how many options? 6. Right? So 6 for the first, 6 for the second. 6 times 6 is 36. That's what they're reciting in like 3rd grade right now somewhere. 6 times 6 is 36. 6 times 7, 42. Now I always remember that because as a kid, it's football. If you score 6 touchdowns and make all the extra points, it's 42 points. I kid you not, this is what I would say. Mrs. Cooper would be like, very good, Ryan. We used to play this game called Engineer. Did you guys ever play this game? This is old school where you'd stand up. They don't do this anymore because it insults the kids who ain't good. And this is back when they wanted you to be fast at everything. Because there were no calculators back in 1990. Well, there were calculators in 1991, but not like they are today, right? And so you'd play this game where you remember it, like you remember your elementary schools. At least when I was there, the desks were lined up in rows. There was no groups. It was just let's all be little obedient little peasants and wave and raise our hand, right? All this crap. You play this game. You stood up next to the person next to you, and Mrs. Cooper would hold a flashcard of like the multiplication of 2 things, and whoever got the answer correct first stood up, got to stay standing up, and the loser had to sit down. That was the way it went. You'd go around the room, and the last person standing won. You know, you'd win like a piece of candy or something. But they wouldn't let you do that anymore because that would hurt the kids' feelings who weren't any good, right? Because God forbid someone realizes that life ain't fair. You know, oh my God, I sound like, oh my God, I'm turning into like an old man now. But nonetheless, we used to play that all the time. And so I used to go home and practice.
You used to have like a sheet to print off, and they would have them all blank.
Mm-hmm.
And like they would time you, and
Yeah, you had to turn it in quickest, right?
yeah.
So in 3rd grade, Mrs. Gallo would do something simple. We used to have these things like they called it the Rizzo machine or something, where they'd give you these dittos, we called them, and you'd inhale them. They smelled so good, like all the fresh ink, probably give you chemicals inside and cancer and stuff. You look. But anyhow, they'd give you these dittos, and Mrs. Gallo's rule was when you're done, right? And so we would just fly through them, and then you could do whatever you want. I'd be in the back of the room making bombs out of Lincoln logs. Like, I always knew I had some issues because I would take the Lincoln logs and I'd build these catapults and fire them across the room and like try to aim it at the kids I didn't like. What a time to be alive. Miss Gallup, like, what are you doing, Ryan? I'm like, oh no. If I wasn't on live right now, I would tell you another story that Miss Gallup used to get mad about us, but I don't want the world to know about that one. I wonder if she's still alive. She was awesome. Mrs. Gallo, what a great 3rd grade teacher. I remember her saying, like, you're never going to know when you need them. We used to get mad because she'd make us multiply like 5-digit numbers by 5-digit numbers. I said, who the hell's ever going to do this by hand? Anyhow, if you're out there, Mrs. Gallo, I love you. What the hell is wrong with me? Some of them are like, what is he saying? Someone's parents probably sit at home or sibling. Like, what is that bearded man talking about? That's me. What a time. Okay, so fair enough. So there's 36 outcomes. Let me remind you this again. We'll bring our picture back up. Here they are. You can count them. 6 times 6 is 36. There we go, right? And so what we need to do is we need to understand. Let's see if I can make this bigger. Probably not. It always takes me to some stupid web page. Now, we want to know what's the probability of getting what, a 7? Is that what we said? 7 and a 4, right? So let me go back to this page. Let me see if I can annotate this. We're going to try. And so where are all my 7s? Well, my 7s are here. Oh, yes, let me do it. I got all these 7 joints right here. How many? Oh, boy, that got ugly. How many 7s can I get? I can get 1, 2, 3, 4, 5, 6. We think it's 6, right? Is that what we think? Looks like there's 6 7s. So, and then what else was the other one we wanted to get? 4. So let's see how many times we can get a 4. We can get a 4 here, here, and here. So it looks like there's 3 chances we can get a 4. Let's just double check for our own excitement. How do I get a 4? I can either get a 2 and a 2, or I can get a 3 and a 1, or a 1 and a 3, right? And then for a 7, how do I get a 7? Well, it's not an even number, so I can't get a pair to give me a 7, right? A 7 has to be a 6 and a 1, a 5 and a 2, a 4 and a 3, and then the symmetric other ones, the symmetries. Yep, right? So we all agree that there's 1, 2, 3, 4, 5, 6 versions, 6 ways to get a 7 and 3 ways to get a 4. I'm having fun with you guys. This is so much fun. We're laughing. We haven't cried yet, but hopefully we don't get to that point. So the number of times we roll a 7 is 6. And then the number of times we roll a 4, that event, how many outcomes are in that event? There are 4 in there, I think. No, 3. I already lost my mind. I lost it. Oh, no. 1, 2, 3. 3. I got it wrong. I'd have flunked. Can you imagine I'd have failed the test? Can you imagine if the professor fails? Okay, so since we have that, then the probability we roll a 7 is 6 over 36, which is a 1/6. And then the probability we roll a 4 is 3 over 36, which is equal to a 12th, provided we didn't make any arithmetic errors. Does anybody have any questions about this? Comments, concerns? My fingers are really cold. I know I told you this, but. Having fun yet? Let me blow my hands. I shouldn't do that. Look, if we can't have fun and joke about everything in this world, what good are we here for, right? Isn't that the truth? You got your penguin hat on. He got his penguin and the little Islanders on. Anybody else have no hats for the rest of you? Just some LaRoche. They give you those masks for free? You have to pay for them.
You to like donate the.
Oh yeah, you donate to the cause. Yeah. What's that? What's wrong? Yeah, you got to. I think you get one for free, right? If you need a free a mask, you just go to Sheets and say, I don't like masks, and then they'll give you a bunch of them. That's how you get a mask. I actually saw, this is the beginning of the Roni, I saw a fight in my local Sheets over a mask. Like, I was like, okay, this person don't want to wear a mask, don't want to. Everybody wants to get their moment where they can film some crap and then put it on the internet for everybody to see, right? Like they're doing some good to society by filming some other jerk. Like, what a bunch of jerks. We got jerks everywhere. This is a jerk-free classroom. All right. Any questions about this fun dice problem? I don't know. Is there not? Now, right now, we're just asking some very basic questions. We're not necessarily, I mean, we might want to ask something a little more involved, like what's the probability we get a 7 or an 11? Or what if the probability if we roll the dice 3 times that our sum is equal to 22 or something like that? Right? That's a little more sophisticated of an experiment. But the idea is we want to be able to quantify these things if possible. Okay, does anybody want to ask a question about this stuff? Okay, so here's what we want to do. So our goal now, well, we're done, right? What time's class over? Yeah, because we started at 12:30, right? Oh my God, this is terrible. We have to quit. I'm crying. You're crying. Now, is that a movie or something? What the hell is that from? All right, guys, does anybody have any questions? We do need to stop. I don't want to make your lives miserable. Yes?
I'm unrelated, but like, why does one horse usually have more than one horsepower?
Why does one horse have more than one horsepower?
Yeah.
I don't know. I don't even know. That's a good question. We should look that up. What's the history of the term horsepower? Is this a joke or is you asking a serious question?
Oh, like a serious question.
Yeah, I don't know. I'm sure at one point or time that they would quantify power using what a horse is. I'm sure it dates back. I could be wrong. It probably dates back to when before automobiles there was horses and buggies. And so that's probably where the term comes from. That's a good extra credit thing. Look it up. Inform us. All right, everybody. Thank you very much. Sorry that I almost kept you late. Be safe. And look out for your homework later. Bye. Love you. Platonically. Bye. Thanks, guys.